So the point to start this day was to give an overview of the recent developments on Spintronics and potential for a new innovation. So this is a general view of what is happening in the community, but also at the European and international level on Spintronics. And the presentation is organized in three main aspects. The first one is challenges for the digital world and the place of Spintronics. I'll go after two main success stories of Spintronics for industrial applications, and also coming back after two more recent developments and their place in the national strategy on Spintronics. I'm just trying to see the pointer. Good. So let me start. So in the actual society, there are some digital and societal transformation which are covering different aspects of the digital world, which are coming from storage, computing, sensing, communication, and this open up new fields of applications which are accelerating in the last years, which are the human-machine interface, smart cities, or the place in health and medicine applications. So these technological advances to come are expected to open up other digital opportunities, and there are several challenges for the digital world. The first one is the energy consumption. So we all know that the digital consumes today, okay, the numbers we can discuss, but let's say something like 5 to 10% of the world electricity. And if we are continuing on the same trend, we can extrapolate that in the forthcoming tens of years to 100%. So there is a problem of energy consumption. There is another point, which is the material criticality. We are also in a geopolitical sensitive environment, but also the microelectronics is using more and more materials. So in all our research, it's important that the materials we are using in the electronics can be sustainable, but also to have a policy to recycle them. And at the European level, there is also a need for a technological sovereignty in terms of having access to technologies which are important for our society. Now, specifically to microelectronics, there are some more technological challenges, which are the downscaling. So we are approaching for some some physical limits. I've mentioned already about the power consumption, which increases, the exponential growth of data, and also interconnecting a lot of transistors in the actual electronics. So let me just give you in the presentation how we think Spintronics can help, but also what are some of the challenges we see on that. So first of all, what is spin electronics or Spintronics? So not all of the members in the audience know what is it, so it's important to see what is it and how this can have an impact on the usual or more standard microelectronics. So regular electronics is using electrons. Spintronics is using, in addition to the charge of the electron, its spin. And by using, instead of electrical currents, some spin currents. So the spin is classically represented as the magnetic moment, which is due to the rotation of the electron around its axis. So using spin currents instead of electrical currents give an additional degree of freedom that could help some application in electronics. So that can have some advantages in terms of power consumption. So all the presentations during the day, you will see how this can help. And also, we can manipulate the spins more efficiently than the electrons itself. Also, in the sense of dynamics, we can do this very fast. Another point which is of importance is that this field of spintronics relies on a material engineering at the nanoscale range. So the fact that there is a knowledge in theoretical aspects, but also in terms of growth of materials in order to take advantage of interfaces is important to engineer materials. And also with respect to the microelectronics, these materials can be looked as a bit more exotic, but the main block of spintronics is an element which is called magnetic tunnel junction, which can be inserted in a regular microelectronic flow. So you can see for people from microelectronics metal levels, and we can insert these magnetic materials as a backend technology on top of the microelectronics. So that's an advantage, and that individual brick, which is magnetic tunnel junction, can be used for different applications, memory, sensors, and RF applications. So there was a trend in spintronics, namely from the discovery of giant magnetoresistance. So magnetoresistance is an electrical resistance which depends on magnetic field or magnetic configuration. So from the discovery of the giant magnetoresistance in '88, which was awarded by the Nobel Prize in 2007, to Peter Grünberg in Germany and Albert Fert in France. So that gave rise to several applications, like in the data storage. For example, there were first concepts of a giant magnetoresistance which were used in read heads rather quickly after the discovery, in data storage, after in sensors, and after in memories. What we can mention that there were a lot of physical discoveries, and France and Europe were on the leading edge of this, which actually contributed to the development from scientific point of view, but also in terms of application. So, of course, there is a new field which can go beyond all this initial application, but my first point in the presentation will be to go over the three different applications which are shown here in data storage, sensors, and memories, and see where we are and what are the outcomes and eventually more difficulties which are there and which do not allow to, have even larger impact on that. Before going to that, so there is a potential for innovation in spintronics already in France. There is a big community and very dynamical. We are at the point at which there are some large-scale investment by microelectronics industry worldwide, and in order to bridge the gap in between the excellence in science and between economic outcome, there is also a network at the European level which is trying to have roadmaps and really bring a European community view on this application, which is called Spintronic Factory. So let me go now to some of the success stories of spintronics for industrial application. So magnetism, and thanks to Bernard for this compiling this slide, has a broad range of applications, which some of them are not really spintronics in the field of permanent magnets, soft magnets. But with the emergence of spintronics, there are more applications which are coming in microelectronics, memory storage, RF, wireless communication, and more recently robotics and artificial intelligence, data storage, and also biomedical. So all these are applications of magnetism. Now, let me go back to the Spintronics. So let's see what are the impacts in data storage. So magnetic recording was the first industrial applications of Spintronics. So, and for, if we are looking to a memory hierarchy in which we have the representation of the storage in between the cloud local storage up to the processor. So in terms of speed and density, in terms of storage, there are solutions which were proposed by Spintronics. For more than 50 years, the R&D in magnetism was largely stimulated by the development of magnetic recording, and these are some physical developments from the 60s that allowed a lot of developments in the field of magnetic recording. So right now, due to the physical limits that I was mentioning, the progress in areal density is slowing down due to some physical limits and lack of some cost-effective solutions, saying that the pattern media maybe are too expensive. And on that field, there is a progressive replacement of flash hard drives as solid-state memories. While saying that, we can also mention that in the actual storage in cloud, there is still a lot of magnetism. More than 50% is still magnetic, namely for magnetic hard disk drives or even magnetic tape or archive storage. And due to the very large increase of the data need in the last years, these magnetic solutions are still of interest and still used. So this is something maybe not all of us are aware. I'm going to a second aspect of main success story of Spintronics, which are the sensors. So we'll have a presentation and overview which will be given by your development, but also some presentation from Allegro and Sensitech on that. So the magnetic sensor, the second major industrial application of Spintronics, so evolved with the Spintronics for the more general AMR, anisotropic magnetoresistance, or GMR, giant magnetoresistant, and more recently in what we call the tunnel magnetoresistance. And there were different strategies in order to have this linear dependence of the resistance of a device as a function of the external field. And this application in magnetic sensor are very large, so we will have the presentation afterwards, but going from position encoders for automotive and robotics, for non-contact electrical measurement to surface control. So there is a large field of application in terms of magnetic sensors. More recently, the field of magnetic memories emerged, so we'll have a presentation today from GlobalFoundries and also from newer developments from Nello, and Yol will also cover the market aspects on the memory. So on the memory side, and this is a nice picture taken from this reference from 2021, showing that there were some scientific breakthroughs in the MRAM roadmap. So MRAM is magnetic random access memory. So magnetic random access memory, going back to our main brick, which is the magnetic tunnel junction, and trying to build a non-volatile memory which could influence the memory hierarchy we discussed. So the configuration of magnetic memories evolved from writing, which were done initially with magnetic fields, after with some effects which are injecting a current through a cell, which were called spin transfer torque, or STT MRAM, and more recently, and you can also have an evolution in terms of time, but also in terms of application. More recently, there was this spin orbit torque effect that actually allowed a lot of improvements in terms of speed of writing, but also in terms of energy consumption. And finally, this very recent magneto-electrical spin orbit concept that Nello will describe more into detail, which will allow, due to the fact that we are using a voltage control, so not anymore manipulating or moving charges, even lower power consumption. So those advances in terms of MRAM are, in our view, helping to reduce the static power consumption, but also to have a role in the memory hierarchy, proposing MRAM solutions at different levels, and replacing part of the volatile working memory by a non-volatile memory allows to switch off all temporarily unused blocks of electronic circuits, going up to microprocessor to reduce leakage. So again, in the presentation from Yol, you will see what is the impact, actual impact of memories, and what are the projections. So this is for the situation right now. Let me now just go to some recent developments and also their place in national strategy on Spintronics. So Vincent mentioned that we are a kind of peer-to-peer exploratoire that are trying to reach this acceleration strategy on electronics and to see whether, namely with the new field of opportunities, if Spintronics can go beyond the several applications that I was mentioning. So in the framework of peer-to-peer spin, so we are trying to namely address these new fields of applications in which we are trying to combine spin with other type of effects. And with respect to the needs of the digital world that I mentioned at the beginning of my presentation in terms of storage, artificial intelligence, Internet of Things, or smart communication, we are trying to, in the framework of the project, to use some Spintronics solutions. So I will not detail them today, but of importance in the project, like skyrmions or terahertz emitters, magnonics, RF, advanced sensor, in order to propose new solutions. So these are started in the framework of coherent strategy, we hope, in the framework of France 2030, and within the PPR, spin, and electronics. So first of all, the challenges for the future of computing. So in the terms of computing right now, we have some difficulties coming from the heat wall, memory wall, or the Moore's law in terms of miniaturization. And we think that the added value from Spintronics is coming at 3 different levels, proposing a better memory storage. So we looked already at the roadmap to see what a better memory can do, to use something like bio-inspired computing, which can bring advantages in terms of power consumption, but also, and we'll discuss just after, doing directly the computing in the memory, because right now a lot of power consumption is coming from the transfer of data between the memory and the processor. So, for example, if we are looking to some numbers, we can see that if we are looking to the energy consumption, addition of data is times 1, access the data is times 60, but accessing the data, which is not localized or is far away from the CPU, is a factor of 3,500. So that's the conventional computing. In an in-memory computing, we want to perform the logic operation inside the memory, which will allow to do local data processing with advantages in terms of low energy. And the fact that memory solution can do that, there are some requirements in terms of speed, in terms of endurance, and in terms of power consumption, and we think the MRAM can play a role in that. There is also Spintronics for low-power bio-inspired computing. So the digital computer with the conventional type of architecture consumes a lot of energy, also due to the back-and-forth data exchange between memory and processing. So taking inspiration from the brain could help us to reduce the overall consumption. So there will be some presentation today from Golana Computing and also Thales that could address these aspects in terms of bio-inspired computing. In terms of bio-inspired computing, except or in addition to the fact that we are proposing some hardware solutions that are adapted, what is really important in the field is to go entirely on the whole chain, going from the physical devices up to primitive circuits architecture to algorithm, and the low power consumption at the end will come not only from the individual device, but having really the design houses or dedicated multi-process wafer flow on which we'll have the new discoveries. And another field, so I discussed a lot about magnetic memories. The main brick of the magnetic memories is this magnetic tunnel junction here. The same type of device can be also used more recently as spin-torque nano oscillator, which could either convert the voltage, a DC voltage, into an RF signal for a tunable RF emission, but also as a spin diode, which will convert the RF signal into DC voltage, and this could have some outcomes in energy harvesting or in smart communication, and these are important fields which are also addressed in the framework of the PPR spin. I would say at the end, the holy grail would be an integrated system on chip that will have at the same time a microcontroller that is integrating a magnetic memory, a magnetic sensor which is nearby, but also a wireless system like a wake-up receiver that will wake up the system only when it's needed and to not consume anymore in standby mode. And having a hybrid CMOS MTG Spintronic system on chip is something at which Spintronic can propose a nice solution. Before going to the conclusions, what is important and specific for Spintronics is that you saw that we have some specific materials. So this main brick, which is the magnetic tunnel junction, is a magnetic is a tunnel barrier, which is an ultra-thin oxide, and we have some ferromagnetic material. So there are some specific tools used for that, for their growth, for their fabrication in terms of etching, and also some specific characterization. So in order to really give an advance to the ecosystem, is it important to have all the chain, including the equipment suppliers, but also to have access through some academic or more industrial pilot lines in order to transfer all this development. So there will be a presentation for equipment suppliers, either from deposition, characterization, but also what is happening in the framework of European Chip Act in the pilot lines. So I will conclude saying that Spintronics is a fantastic playground for innovation. So there were several success stories in the last years that moved from sensor magnetic recording MRAM. There are opportunities, namely, I think, with the wave of artificial intelligence, the fact that we are able to propose a low-power hardware is very important for this field of low-power artificial intelligence. We think that as a community, as a French and European level, we have all the ingredients from scientific point of view to transfer this innovation to economical gain. The day here is important to put together, I mean, the science together with industrial players. We have some invited guests from the ministry, and I think it's important that at the end of the day we identify not only the opportunities, but also to see what, from the respect to the excellence of science right now, do not allow to even go at a higher level in terms of economical impact. So I would like to thank you for your attention. So if there are some questions, maybe at some point we can also display again the answers on what are the difficulties, on obstacles of Spintronics.
So good. I just had one question regarding power consumption. In the beginning of your presentation, you said that Spintronics allowed low power consumption. Could you elaborate on the why it's so interesting for that point?
Mm-hmm. Yeah, so this is one of the keywords which was used also for our pepr. So there are things that are clear, I mean, in terms of just looking in the field of memories, for example, you take and you compare side by side with respect to existing memories, and you see the numbers, and there was an evolution between the initial configuration, which gave some numbers, but after you can further improve by manipulating more efficiently the spins than the electrons. So the fact that you can have a local access to manipulate the electrons through their spin gives more efficient control of the electrons, and at the end this translates in what is needed for energy per bit in order to write the information. So in the presentation, namely for, so it is clear for memory. Now, when you can do something like bio-inspired, you can gain other orders of magnitude, but you have to have a hardware which is adapted. And doing what I mentioned, the in-memory computing is a kind of architecture. The fact that you are not transferring the data is also giving some gains. So the power consumption is something like integrated between the hardware itself, controlling more efficiently the spins, but also using these hardwares in an efficient way.
I appreciate your talk, certainly. But it's also a permanent question. How you make this new technology compatible with the silicon, with all we know what it is done?
So clearly, this is one of the fears or obstacles of the standard, more standard microelectronics, because you are integrating some more exotic materials. So what I mentioned was more cobalt, iron, and so on, but you can have also some platinum, ruthenium, and so on. So in terms of integration, the fact that you have this magnetic tunnel junction, which is the main brick, that you can integrate as a back-end process on top of existing microelectronics, separate all the fears concerning contamination of materials. But I think there is still the fact that big foundries transferred already these magnetic materials, and they saw that they can isolate properly the use of these materials is already a positive thing. But yeah, we really have to say that this is a back-end process that could be separated from contamination point of view. Now, is a new technology, and for any new technology, having new materials, you have to really bring major breakthroughs in terms of energy consumption and so on in order to promote the technology. The fact that these Spintronics can be generic, not only for memories, but also for sensors, for RF, could be an asset in order to promote it as a generic technology that could help many fields of microelectronics, not only the memory. So, but we have to play with that, and I think it's important to discuss with all the people around in the industrial ecosystem.
Concerning companies, the most of big companies of modern technology are not European. So let's suppose that we succeed in Spintronics. Do we have to create new big companies to have large distribution, or we have to sell what we produce to?
Is a very good point. Clearly, and not only for Spintronics, there is a sovereignty strategy at the European level in which actually doing the excellent science, but which at the end ends up in economic development in Asia and US, was for the moment the outcome for Spintronics and for other technologies. So the different type of application mentioned here, some of them are mainstream for microelectronics, so very advanced technological nodes, and clearly at the European level, we do not have the big players there, so we are still relying on what TSMC or Samsung is doing. So there is clearly a political decision to be taken, so we hope that the European Chip Act is going into the right direction and has sufficient impact to promote the development of big foundries at the European level. Without that, clearly, namely for what is memory and artificial intelligence, we are out of the game. For the other applications, namely for sensors, so Europe had a play to role. We hope that what is happening with the electric cars is not changing the game, because that would be a disaster for Europe. So on that, you do not have to have the the most aggressive technological nodes for that. But even for that, I mean, there are some added value of what the community can bring in terms of sensor for automotive. And clearly, I think the biggest impact in the short term, I think, should be on that. European Chip Act for a European strategy in order to compete, plus using the automotive market, which is strong in Europe, I think, are the answers to your question.
Thank you. I think we should. Good. One last question.
Comment.
One word to go after the response from Lucian and answer part of the question from Alain. Is chip GU very important to have this big foundry in Europe, and that this big foundry in Europe will accept the materials that are needed for any type of spintronic technology. So there is also some action to do, and this is right now. This is the moment to do it. For the long term, to integrate the options to have the spintronic technology in these European foundries.
Okay. Yeah, we have to move forward.
Let's go.
So I don't know if we can project now the answer for WooClub or not on the second question, or we'll do it later the day?
Yeah, maybe later.
Later, okay. So, thank you very much.